Hello and welcome to AI for Developers. I'm Chaitanya talking bot. Today's lesson is titled Variational Autoencoders. VAEs. AI that imagines new data and learns its essence. Hey there, future AI builder. We've seen AI that can recognize cats, translate languages, or even play chess. But what if AI could create something entirely new? What if it could draw a cat you've never seen before, compose an original song, or even design a new chemical compound? That's exactly what variational autoencoders, or VAEs, are all about. Think of them as the creative artists of the AI world. For you, the developer, understanding VAEs means unlocking the power to build applications that don't just process data, but generate it. Before we get to imagination, let's talk about its simpler cousin, the autoencoder. Imagine you have a giant image file, and you want to shrink it down to its essence without losing too much detail. Then expand it back. Encoder. This part takes your input, like an image, and compresses it into a smaller core representation. We call this the latent space or bottleneck. Think of it as a smart zip function decoder. This part takes that compressed essence and tries to reconstruct the original input as accurately as possible. It's your unzip function. Developer perspective. You train an autoencoder by showing it many inputs and making it learn to encode. Them to a latent underscore vector and then decode. That latent underscore vector back to something almost identical to the original input. Its goal is to minimize the difference between the original and the reconstructed output. A regular autoencoder is great at reproducing what it's seen. But here's the problem. If you try to make it imagine something new by just giving its decoder a random latent underscore vector you'll often get garbage. The issue. The essence space, latent space, of a regular autoencoder can be messy and have holes. Points that are close together in this space might represent very different things, and many points might represent nothing meaningful at all. Analogy. It's like having a map where some areas are well-defined towns, but between them are vast, unlabeled wildernesses. If you randomly drop a pin, you'll likely land in the wilderness. Developer perspective. If your decode, random underscore latent underscore vector, function gives you static or corrupted images, it means your underlying latent underscore space isn't organized in a way that allows for creative, meaningful generation. We need a smooth, continuous idea space. This is where the variational part of VAEs comes in. Instead of the encoder compressing an input into a single, fixed point in the latent space, it compresses it into a distribution, essentially a range of probabilities for where that essence might lie. Probabilistic encoding. For each input, the encoder generates two things for each dimension of the latent space. A mean the center of the distribution, and a variance how spread out the possibilities are. Analogy. Instead of saying, the car's essence is at point X a VAE encoder says, the car's essence is somewhere in this fuzzy cloud around point X the goal. By forcing the encoder to represent inputs as these fuzzy clouds, and then gently pushing all these clouds towards a common, simple distribution, like a perfectly round, centered blob, we force the entire latent space to become smooth and continuous. There are no more holes. Developer perspective. Your encode function now returns latent underscore mean underscore vector, latent underscore log underscore variance underscore vector, instead of a single latent underscore vector This extra information is key to organizing the latent space. Let's trace the journey of data through a VAE during both training and generation. Step 1. Encoding to a distribution. An input image, e.g., a handwritten digit, 7, goes into the asterisk encoder. The encoder doesn't just output a single, 7 essence vector. Instead, it outputs the backquote mean backquote and backquote variance backquote for a probability distribution that represents the essence of this particular 7. Step 2. Sampling from the distribution. From this backquote mean backquote and backquote variance backquote, we don't just pick the backquote mean backquote. We sample a point. This little bit of randomness is vital. It encourages the VAE to be robust and helps create the smooth latent space. Think of it as drawing one specific 7 essence from the cloud of possibilities. Developer perspective. In your code, you'd calculate backquote latent underscore vector equals latent underscore mean plus express 0.5 asterisk latent underscore log underscore variance asterisk epsilon backquote, where backquote epsilon backquote is a random vector sampled from a standard normal distribution. This step injects the variational noise needed for imagination. Now that we have a sampled backquote latent underscore vector backquote, an essence point, it's the asterisk asterisk decoder's asterisk turn. Step 3. Decoding the essence. The asterisk decoder asterisk takes this sampled backquote latent underscore vector backquote and tries to reconstruct the original input image. During training, the VAE learns to make this reconstruction as accurate as possible. Asterisk the magic of generation. Because the entire latent space has been forced into a smooth, organized continuum, thanks to the variational part, we can now simply pick any random point from this well-behaved latent space. Developer perspective. Feed backquote decode backquote with any new, randomly generated backquote latent underscore vector backquote, e.g., a simple vector of random numbers drawn from a standard normal distribution. And it will reliably produce a plausible, novel output, a new face, a new song segment, or a new molecule. This is how you implement AI imagination. How does the VAE learn all this? Through a special loss function that tells it how well it's doing. It has two main components it tries to minimize. Asterisk 1. Reconstruction loss. This is like a regular autoencoder's goal. Make the output look as much like the input as possible. Did I faithfully recreate the input image? Quote, e.g., mean squared error. Asterisk 2. KL divergence loss. This is the variational magic. It measures how much the encoder's output distributions, those fuzzy clouds, deviate from a simple, standard distribution, like a perfectly centered, round cloud. This forces the latent space to be continuous and well organized, preventing those holes. Is my essence space tidy enough for imagination? Quote, developer perspective. Your total loss function is typically backquote total underscore loss equals reconstruction underscore loss plus beta asterisk KL underscore divergence underscore loss backquote. The backquote beta backquote value lets you control the trade-off between reconstruction accuracy and the smoothness of the latent space. Optimizing this loss function is how your VAE learns to be both good at reconstructing and imagining. VAEs are powerful tools for building creative AI applications. Generative art and media, creating realistic new faces, landscapes, music, or even short video clips. Drug discovery, exploring latent spaces of chemical compounds to design novel molecules with desired properties. Anomaly detection, if an input doesn't reconstruct well, or its latent representation is far from the common distributions, it might be an anomaly. Data augmentation, generating synthetic data to expand limited datasets for training other AI models. Developer perspective. VAEs move beyond just prediction and classification. They empower you to build systems that actively create and explore data, leading to exciting new possibilities in design, science, and entertainment. Thanks for watching. If you found this helpful, make sure to subscribe to our channel and hit the like button.